I will get us started. As you guys probably anticipated, we are moving on to the next chapter. I hope the homework on 35 went well. In fact, that's where I'll begin, kind of a quick review there of 35. But even before I get there, let me give a couple things back. I've got 4 more folders here, and I thought I would just kind of twist them around so you can kind of scan through them. And the same as before, if you find it great, take it. If you don't want to mess with it here in class, that's fine too, and I'll just throw them over into the lab and you can find them. And I trust you still have the link and that you can check to see as things get recorded. So I'm more caught up, but still got a long way to go, and hopefully got to start thinking ahead here as we've got something like about 6 weeks left here in the semester here. And so as things get closer to the end, I want to make sure things get or I get caught up, or at least as much as I can before finals there, get that stuff back to you so you can see that it's recorded. Also, I want to pass out, so I want to give that a little chance to go around, one of these forms. Please grab one, actually maybe to separate them out. I will put one over on this side. Grab a form, and sometime, not necessarily today, but if you have time during the lecture and you're bored and not listening to me talk, you can fill out this little form. But it was more of a thought process on yours and to give back to me. But this is nomination forms for the Outstanding Faculty of the Year. You may or may not be aware that our school each year takes nominations and lists the outstanding faculty of the year. Now, keep also in mind that faculty members can't win it twice, okay? And so I feel more comfortable passing it out because this is not self-serving for me. Don't nominate me. You can't nominate me. I already won years ago, so it's on the list. And on the front are the faculty members. Some of you may know, and some of you may not know, since many of them have since retired. But anyways, those can't be nominated. But I wanted to take this opportunity to give you a chance to think about this, and you can see that the due date is on the 30th. So I wanted to pass it out for each of my class, you guys being the first one here. And so think about the classes you've had, and I volunteered to be the representative for the science people to pass these out, since it's always a little uncomfortable for other faculty members to do it because it sounds a little self-serving there. But in my case, I can't be nominated. So I go, okay, I'm going to go, and starting with you guys and all my classes. All right. So with all that said, I hope that 35 went well for you. I would describe 35 as this. I'll put it on the board here to kind of give a quick summary. We did 2 things really in 35. The first one was, okay, what if you had a mirror? And maybe I shouldn't even say mirror at this point, because that's about what we're getting started here. I should say we have some kind of reflecting surface. And you have just one beam. And if that one beam were to come in and strike the mirror, and so here's this light beam, and it were to strike the mirror at some angle of theta, and again, measuring the angle from the normal, want to keep emphasizing that. We don't measure it between the ray and the mirror, but between the ray and the normal. The ray would bounce off such that the reflected angle, which we designated with A prime, is equal to the incident angle. And we called this the law of reflection. And so we talked about that first, I guess it must have been a week ago, and said, okay, this is one way of controlling the light. And that's what I want to emphasize in chapter 35, is controlling the light. Forming images now is our next step. How do we make something bigger? How do we magnify it? How do we make it smaller if we wanted to make it smaller? How do we change its appearance of its location? All of these are done by controlling the light. And so what you learned in chapter 35 was the 2 techniques for controlling the light. One is reflection, one is refraction. So this is reflection. The other one you learned was, what if you had a surface where the air, or a medium I guess I should say, where the air can transmit through, and it can go from one medium into another, say air into glass, or water into glass, or air into water, or whatever the interface is. But at that interface we learned that again the light would have some bending to it, some redirection with it. We call this Snell's law, and last Thursday we went through some derivation and said that, okay, look, if you have a beam of light coming in, so here's this beam of light, and again it is incidented at some angle, theta 1, okay, so there's our incident angle again. This time, of course, it goes into the material, so it doesn't reflect off, it goes into the material. But we learned that because of the change in speed, there would be a bending, and of course towards the normal if it slows down. And so we did learn that in glass, which I will call this index number 2, as opposed to where it starts with index number 1, we learned that glass slows light down more so than air slows light down compared to a vacuum. And we learned the numbers. Let me not repeat the numbers here, but the point is we did learn that there would be a bending of the light, what we called a refraction of the light. So the whole point of 35 was reflection and refraction. And the mathematical relationship was this, that n1 sine theta 1 is equal to n2 sine theta 2. And so there's my second little box. And those were really the two things that we learned in chapter 35. And I said, if you know those two things, which is the physics part, together with your math, and we did some problems that had trig, and we did some problems that had a lot of geometry. And I know if you've done the homework, you saw a lot of geometry in there. There's some, and then there's some tough ones, not so much tough in terms of the geometry of the math, but just drawing the rays and seeing what the rays are going on. I think that one that asked you for the apparent radius of the sun is a good example of the bending of the light. Or how long is an optical day compared to a geometric? Both of those are good ones where you got to get into some geometry. And both of those were based on the bending of light as we went from outer space, a vacuum, into the atmosphere of air. Well, we're going to continue on. And so hopefully you got your feet wet and started remembering all that geometry, because it's going to get a lot worse here. And so what is 35 here? 36, thank you. Chapter 36 is entitled Geometric Optics. And I would describe 36 really as a continuation of 35. It is really what we were after here. These two fit together, hand in glove. We're going to kind of switch gears, still stay in optics, but switch gears when we get to 37, as you will see. So 37 and 38 go together really well, but they focus more on the wave nature of the light, not on the ray nature of the light. And so these two chapters on the rays, and then of course controlling the rays here, and that's what geometric optics is all about here. So let's start with this. Let's start with this whole idea. Let's say I have an object that I'm going to look at. Okay? And in my case it would be you guys, and I guess in your case it would be me. You're going to look at something. If I was outside, it might be that tree over there, or if I was out on the bluffs, it might be a sailboat out on the harbor there. And go, okay, what am I looking at? And if you look at something, you will probably notice something right away here. If this is my object, and I stand to the left or the right of it, I can see that object. What does that tell you about an object? Yeah, and so the first thing is that the light comes from the object, and it is coming in all of these directions. Okay? Well, of course, if it's dark, fair enough. But the point is, if when it's daylight, if I go stand on the bluff over here to the east or to the west, I can see that sailboat, right? I can see that plant over there, right? The light goes in every direction. In fact, I would take one step further even. I would be able to even tell you something about the distance that it is to that object. I could tell which students are close to me here in the front row and which students are far in the back row. I bet you can tell whether I am forward of this desk or behind the desk. So that's really the part I want to focus on. Number one is you see an object because the light comes from it. Fair enough? And then how do you get the distance of that object? How do you get what we might call your depth perception? And this is the key for this chapter to make any sense. What? Yeah, it's why you call it binocular vision. It's why you have two eyes. Those two eyes are there because your brain is going to take one ray, which will go into, say, your right eye, and you'll take another ray, which will say goes into your left eye. And so if this is a person watching it, this would be one eye socket. This would be another eye socket. Yes, this would be the top of their head here. I can't do this anymore. This used to be my hairline. Now I shave it. Bummer. I don't know if that's good or not here. But if somebody were to look from the top, that's kind of what they would see, at least the best artist that I am, right? But what I want to emphasize is that binocular vision. And for this to make sense, it's those two rays. It's that binocular vision. So as I look at something close, like this drink right here, the rays come out and my eyes are tilted in at a tighter angle than if I look something in the back of the room. I look at that fire extinguisher. My eyes have changed that. And you and I have learned over the years of how to adjust and read the light. How to get a feel for how far is that light. And so now you have a depth perception, and you probably don't think much about it. Some people's are a little more sophisticated than others, but I'm sure all of us can probably drive a vehicle. That's one of the tests when you learn to get your license. You have to sit there and you have to do an eye exam, and one of the things they usually do is they put an object at a distance and they ask you to say which object is further away, with the idea that if you're driving a car and you're going to make a left-hand turn, you need to realize how far away is that car? Do I have enough time to safely make a left-hand turn in front of it, or should I wait for the car to pass? And so that depth perception and understanding of where it is very important. And the physics I want to start off with is, again, binocular vision. The whole reason you have two eyes. And you can see it in the animal world. For those of you who like biology, I mean, your predators have their eyes more towards the front of their head, right? You've got all the cat family and the humans and the birds of prey. They all got their eyes on the front of their head. And the idea is, by having the two eyes here, I got a good depth perception. I know where that prey is. I know how far it is. But there's a sacrifice that we pay by having our eyes in our front of our head, which is what? Yeah, we only see forward. We don't see our behind us. And so other animals, say birds of non-prey birds, their eyes, tend to be a little bit more rolled over to the side of their head. So one eye can see over here and look for the predator, and one eye can see over here and look for the predator. But then what sacrifice do they pay? Yeah, that depth perception. And so, this little sparrow sees me walking, and okay, there's that evil teacher. But they're not really sure how far evil teacher is, so they just take off. And I'm 20, 30 feet away, not even caring that there's a sparrow over on the side of the road. I'm just trying to walk home. But it'll take off because it just knows there's something that can do some harm to me, and it catches that. Now, its eyes are curved a little bit, if you look real carefully, just enough so that it gets just a small depth perception, so that when it pecks on the seeds, it knows how far it's supposed to put its beak down in order to pick up the seeds. And maybe I'm getting too carried away here, but what I really want to get at is depth perception, binocular vision. Because without that understanding of how we get depth, you won't understand of how we get images when we control the light, when we put them in lenses and mirrors, which was what we're...
So it's impossible to look straight?
Possible to look straight?
Possible to look straight, like you're always having to... Never mind.
Okay, yeah. Yeah, so your eyes are always, you know, pointed in a little bit, but obviously the farther it gets, the less they're pointed in. So if you're looking at the moon, you know, I would say your eyes are straight. They're pretty straight by that. And you'll see that when we do our optics here. We will define about, you know, how far does something have to be before we say it's parallel. And we'll do about 30 feet. So we'll say infinity is 30 feet and beyond. Anybody ever ask you how big infinity is? Now we'll have an answer. Yeah.
What about people that are stereo blind? It's like
stereo vision is another way of saying binocular vision too. Yeah.
It's like I was diagnosed with stereo blindness when I was like 16.
Right.
But I can still tell how far away things are with linear perspective. So what's the difference between those two things?
Okay, good point. She's adding that there's really more to seeing depth than just your binocular vision. You see that on a TV screen, you see that on a painting, because what an artist will do when they're making a painting is if you were to have overlap. In other words, even if you had one eye closed, I bet all of you could tell me that I am standing in front of this desk. And if I stood back here, even if you had one eye closed, I bet all of you could tell me the desk is in front of me. Fair enough? And that's overlap. So there are other ways that you get this perception of depth. And that's one of them, overlap. Size is another one, relatively sizes. If an artist was drawing a picture and they had two cars in the image, which you know cars are relatively the same size, but they draw one really big and one really small, then that's way your brain is saying, okay, that one is represented far away. Does that make sense? My neighbor's a good example of that. He's older, retired gentleman, and but he's only got one eye. And I was talking with him one day a couple years ago, and well, it caught my attention. I mean, obviously, you know he's missing one eye. That's pretty clear. But what caught my attention was he said, oh, that was the... Well, number one, he drives, and he drives really well. And number two, he made a comment, yeah, it was the best thing that ever happened to me in my life, which I thought was really weird. But I guess when he was 4, he's playing with a knife. And like kids will do, he's pulling and cutting something, and he goes, stab himself in his eye. So he lost his eye. But he said it was the best thing because when he was drafted for World War II, he didn't have a combat mission, and they paid him to go to school to become a civil engineer. So he came from a poor family, had no money, had no way of going to college or anything, and he ended up being a civil engineer, worked for down in the city of Thousand Oaks for it. Anyways, but I'm always amazed at how really significant his depth perception is. He drives a car, and I was asking him about it, and he was all, yeah, I could tell, and he was pointing some things out. But then he was also helping me add shingles onto my roof. That was funny. I wouldn't tell him. But he goes, oh, I'll help. He's a very helpful guy. He'd always come over. And so I was laying the shingles down, and he'd help lay them down, and we'd get out the nails, and I'd hammer them in. And he could not hit a nail. There was just no way he could hit. He would go, bam, oh, bam, oh. And he was getting really mad. He goes, I'll tell you what. I will lay them down. And so he would lay them down. And that's what started this conversation. And so we were just working together. He would stand there and lay them, and I'd hammer, and we were working along there. So, but that's your stereoscopic vision. And some people's brain have adjusted better than others. Athletes usually have that depth perception down well. You know, they see right away, bat coming off ball, there it is, a moment later, there it is. And that means to them, within that fraction of a second, that ball is either going to go in front of them, so they run forward, or that ball is going to go over their head, so they're running back. And so real quickly they can get that depth perception and motion and process it. And, you know, not everybody's depth perception, and it sounds like Your your binocular isn't so.
I guess I don't understand
Good.
because I don't know what it is.
So.
Well, I've never had it.
Yeah. Okay, well, anyways, fortunately, you won't have to have it to do this. We're going to do geometry. But did you notice then I'm drawing two rays? And that's what I want to emphasize. Because watch this now. This is our beginning picture here. Let's put a mirror and an object. So we'll have O represent the object here. So if I were to come over here, is there another one around here? All right.
It's up there.
There's one behind you.
Yeah, you always try to X those three.
There's one behind me?
You have the projector. The eraser. He's talking about
Oh, I'm talking about an eraser. No, I'm afraid to put too much on. Ah, good. Much better. Okay. All right. So if I were to draw a mirror, and I want to emphasize this because we're going to start real simple and it's going to get real complex very quickly here. Okay? But if I were to draw, as the author labels here, a mirror, a flat surface, a reflecting surface, and I would start with an object. And so that's what this whole discussion was about here. I start right here with an object. If I were to stand over here and have a left eye and a right eye. Okay. What would I see? Could I see the object? And what else would I see?
It's reflective.
Okay. And of course, you've stood by a mirror, you've seen a reflection. You see what we're going to call an image. And that's what this picture is trying to say here. And so if this was, say, you this morning getting ready, you probably were in the bathroom, there probably was some object, maybe a tube of toothpaste on the counter, you probably could look right at the object, and the light would come to you, and you would have a depth perception and say, how far is that tube of toothpaste? And you are looking at the real object. But there is another way of seeing that object. How else could the light get to your left and right eye? Hit the mirror and bounce off. And to your other eye, it could hit the mirror. I kind of missed the other eye there and bounce off. But if this is theta 1, then this is theta 1. That was the last chapter we did, right? Those two angles would have to be equal. And so if the mirror was located at the correct spot so that the light could leave the object, it would bounce off and go to my left eye. And for that matter, if there was more to the mirror, so that this one, and maybe call it a slightly different angle, theta 2, and then this angle, which would have to be identical because of the law of reflection, theta 2, then that would go to my right eye, and what I would get is two beams coming to my eyes, and then what would my brain do? And I'm hoping this first image here shows it really well, although they kind of just show one eye here. But as I look at this ray, and they've drawn three rays, your brain uses its binocular vision and says, okay, let's trace those rays back. And where does your brain say the light is coming from? Well, in this case, it looks like it would be coming from a spot behind the mirror, and it's of course not really coming from there, and so we will call this an image. And so I'll use a little star for my object, I'll use a little circle there like he does here for the image. But again, probably not a surprise to you because you've done this many times already in your life. although some of these other mirrors I think will be a surprise to you. But this first one, this very basic mirror is just, okay, big deal. I see light coming from the object. I see light reflecting off the mirror. But the light has to reflect just right so that you get it converging back to a point. If those lights, all those rays, don't converge back to a point, then it would look blurry to you. You would not get an image. They have to be just right. So only certain shapes are going to work out just right for the light to come back and to hit in such a way that all the rays, and I've only drawn 2 rays, your author's gone a step further and drawn 3 rays, but if all 3 of these rays, and in fact all infinite number of these rays, act as if they are coming back from that point, your brain would not know the difference between light really coming from here. In other words, if there was no mirror and an object really here, if the tube of toothpaste was really here with no mirror, you would see exactly the same thing. And so this is what I mean by controlling the light. And this is what I mean by calling this an image. There is not really an object here. And so our first definition here is what is an object and what is an image. And an image is simply this. It is simply the same structure to the light as if it was coming from an object. But there's not really an object. The light was redirected. And in this case, it was redirected by a mirror. In fact, it was redirected by what we'll call a flat mirror. And most of us are very familiar with this situation, a flat mirror. But they're going to get more interesting when we have curved in, which we'll call concave, or curved out, which we'll call convex. And so what happens to the light? And you can see now, it comes down to some geometry. And so we're going to draw these rays. We're going to use the law of reflection in this case, and then also refraction later on. And we're going to figure out where does the light appear to come from. And when we figure out where the light appears to come from, we will say that is our image. And so, let's start there with the simplest of mirrors. A flat mirror. And by flat, I mean geometrically it's a plane. It's got no curvature to it. It's not this case. It is the ones you are familiar with. A nice flat piece of glass with reflecting. It's like this big one here. A nice flat piece of glass here. And so if I put an object here, so there's my object. And I say, I am going to make an observation. In fact, let me not even draw the person making the observation, because then you're going to want me to draw the rays to go right to their eyes. And so I want to have some freedom with drawing different rays. Notice that all the rays go from the same point. So let's draw the ones that are easiest to work with. Because here's my first question. Where is the image? Yeah, and okay, most of you see it right away. It comes out, what you said, symmetric. Watch this for a moment. What if I were to draw the ray that went straight into the mirror, hitting what I would call perpendicular to the mirror, or in the case of our angle of incidence, I would say the angle of incidence is 0. Where does that ray go? Yeah, straight back. And I'll pretend it doesn't really hit the object and kind of goes on the other side of the object. Okay? So that's where one ray would go. Let me draw another ray. Why 2 rays? Because what do we need to know to figure out where the image is? Yeah, that stereo vision, that binocular vision. We need at least 2 rays. So I will draw a second ray. How about this one that does this? And it hits at some angle, and I'll just call it theta 1. Doesn't have to be a particular angle. But where would it go when it reflects? Doesn't it go off there at that same ray? Notice there where I used the law of reflection. And so these are the 2 rays. So let's say this ray goes out and goes into my left eye, and this ray comes out and goes to my right eye. Where would I say the light is coming from? Well, sort of like this one. I would trace it back. Now these are a little harder to trace, that's why I picked these two, because this one would have the appearance of coming from over here. Right? This one here would have the appearance of coming from here. So those two rays appear to come from right there. So I would say there is the image. And again, hopefully it's the same thing that your author has here. Where is it? Well, if you kind of look at this and do a little geometry, I think we can figure out where this image is. It kind of looks like the image must be on this same line. So wouldn't the image be at the same height here? It wouldn't be like a little lower or anything, right? In fact, let's do a little geometry here. And maybe I should have drawn the normal in a different color so we can kind of see some angles here. But I got this from the physics. This is the law of reflection. From geometry, I will say then that those two angles are equal. When two lines cross, that's what in geometry you call vertical angles. So vertical angles are equal. So I would say that angle there is equal. Now, the reason I care about that is because this angle here would be theta 1. Because again, if I draw a normal and I draw this extended ray, which again we said was perpendicular, aren't these two rays parallel? And so again, going back to our math, we would call these from geometry alternate interior angles. Sound familiar? And so two rays that are parallel means when you do a transient, right, the alternate interior angles are equal. So that would be theta 1. And I could do the same thing on this side over here. That angle would be the same as that angle. I guess I would also say that is supposed to be a right angle and that's supposed to be a right angle. And so as I look at two triangles up here, and I look at this triangle right here, kind of highlighted in blue, and I look at another triangle highlighted here in red, that angle and that angle and that angle and that angle are equal. So I have two of the three angles equal for sure. What means about the third angle? Yeah, they have to be equal. Why? Because the sum of all the angles of a triangle are 180 degrees. So you can see I'm taking a little time to do some geometry here, right? I'm reminding you of your geometry. Because that's how we're going to prove all these things here. And so now I have three of the angles equal. In fact, a little geometry, if all three angles are equal, what would we call those two triangles? Similar, right? But I would even say these triangles are more than similar. Because let's go one more step. Don't they share a side right here? So isn't the length of one side the same of each of those triangles? So what does that tell me? They're congruent, right? And what do we mean by that word congruent? Yeah, not only are all the angles equal, but all the sides are equal. Okay? You would say they look exactly the same. They may be rotated slightly different, but they are exactly the same size, the same dimensions, the same length, the same angles. And of course, one of the theorems you learned from your geometry was if you ever have an angle side angle corresponding to an angle side angle, then all the others have to match. So if those three match, the other six match, right? And so that would say those two are equal. Now, why do I care about that? Well, again, what am I trying to find here? I'm trying to convince you that we have an image that is formed. And not only is an image formed, but I know its location. And so what is the location? After all this geometry, what is the location of the image, say, compared to the object? Same distance back inside of the mirror that the object is in front of the mirror. Let's put some notation on the board here. We are going to use the symbol P for the distance the object is from the mirror. We will then use the symbol Q for the distance that the image is from the mirror. And in this case, inside of the mirror. And so we have just gone through the easiest of the cases we're going to see. What would we say about P and Q? Yeah, P equals Q. Right? Or at least I should say their lengths are equal. Because as you see, we will apply signs to this in just a second. And we are going to call anything on the inside of the mirror negative numbers and things outside of the mirror positive numbers. So more on that coming up here. But at this point, P is equal to Q. The position of the image is just as far in the mirror as the object is in front of the mirror. And I hope you caught that here. You could probably see it well in this case here, right? If I take this, and of course this is a big class, but I put a flat mirror up here with an object in front of it. This object is about 20 centimeters in front. But if you look in the mirror, and of course it depends where you are sitting here, and so if you can look into the mirror, when you see the image, in fact maybe to help out I'll do a couple other images there, okay? But can you convince yourself that the image you see is not on the surface like a painting? Where is the image? Yeah, it's behind it. It's inside of it. And in fact, to help illustrate that, I deliberately picked a mirror that only went this high, but an object that it was higher. Because if you look closely at that image, and you spin it around, the top half is a real object. It is behind the mirror. And if I got it right, it's hard to tell. Because this bottom half, or bottom 3/4, is an image in the mirror. But the top quarter, or less, is actually a real object again. And it is behind the mirror. And you can see its location. And in fact, it looks best, and I wish I could have everybody look in the mirror, or maybe I'll just point it that way, and then move it. Because now you really see that the image created in this mirror is not on the surface of the mirror. Your perspective of it is inside of the mirror, from behind it. Somewhere over here where the light rays never really were. They appeared to come from there, but they never really did come from there. And so we're going to take one step further, and we're going to call this, not only is it an image, but it is a virtual image. Meaning these rays didn't really come from there. And I also want you to see in my drawing, as well as your artist's drawing here, or your book's drawing, notice the dotted lines. What am I trying to say with the dotted lines is, as somebody stands over here, the solid lines represent the real light, where the light is going. Where it came from and where it is going are solid. But the observer over here is going to get the perspective as if they have been coming from this point. And so hence dotted lines back there. And that's a virtual image. Real images, the light will really come from that spot. And those aren't quite as common, so you may not have seen them. So I got to build up to real images. Most of us are very familiar with the flat mirror. That's why we start there, yeah.
So even with one-eye curves, you can still see them line up. So this doesn't demonstrate the stereo vision or the depth that you're talking about.
I would say not completely, but your brain is filling in the missing pieces. You are not getting two rays when you have one eye
We
closed.
wouldn't be able to tell if it was on the surface or a foot behind the mirror, even with two eyes, because it's too hard to tell.
Oh, you mean because your eyes maybe aren't far enough apart to tell a difference?
Right.
Okay, fair enough. fair enough. Yes, so your stereoscopic vision becomes better the further your eyes get apart, definitely. That's why if you, well, you were in the Air Force, I don't know if the Air Force uses it, but the Navy does, where they've got a nice set of optics on board where the observer puts their eyes into there, and then the mirrors reflect the light out to the width of the ship. And so as you look forward off the ship, you can get depth much better, besides magnifying it with binoculars and stuff. But you can really get that depth perception and where the distance is. It's why we as scientists have telescopes in the northern hemisphere and the southern hemisphere. So we can observe and compare the images we get and to get a depth perception. It's why the IMAX and the stereo vision stuff, you know, when they're doing that IMAX filming, they've got the two cameras mounted, taking one image, taking another. And then when they go and they play it back, they play back both images. And you put on the special glasses that let one image go to one eye and one image go to the other eye. So each object sees a little different. And it's three-dimensional now. But even without the 3D vision, I mean, movies look pretty 3D. Because my brain kind of fills in the missing pieces. But it's not a true 3D until I get a different image in my left and my right eye. Yeah?
So wait, you can break that depth perception, like you're like get images from this far, like very far apart from Earth on the Navy, something like that?
Yeah. So, well, they go, because you get one image here and, you know, one image there.
It's not only like this, for this much distance between the eyes, not...
Well, yeah, so you'd kind of have to learn a little bit more about this. You would have to be able to look in there and realize that I am not looking at the difference between something that's in a room. I can tell how much further something is within this room range. But what you're getting at is, you know, when it gets really far away, I have a difficult time telling which one is further. When I'm in my car making a left-hand turn and I see two cars, you know, they're way out there, I'm not sure which one is in front of the other. I agree.
I was just saying, we can't tell that if it's flat or it has depth.
From there?
Yeah.
Okay, fair enough. But if you were standing here, you could.
Yeah.
This might be a dumb question, but if I covered one eye though, and you moved the real object that's behind the mirror back a greater depth than the front object is virtually in the mirror, would I be able to tell the difference?
Well, cover one eye, can you?
So I guess not. I guess this is the movie side to side.
It's hard.
Yeah.
Yeah. You know, if I were to hide the extension of my arms so you can't see them, and you were to cover one eye, you know, tell me when to stop when these two are at the same distance.
Yeah.
Okay, now open your eye. Yeah, and I heard some four-letter words there. So obviously, you get that idea that there is that little bit of depth perception. But even with one eye, again, you can see depth, like on a movie screen. You do see depth. So I don't want to leave you the impression, because size and overlap and shading and the reflection of the light, the coloring of the light, I mean, all of those add to depth perception, as well as stereoscopic vision. And as well as your brain filling in the missing pieces. That's what makes movies nice. Because the movies, they're just throwing up 24 pictures every second. And boy, it sure looks like that car's driving down the road. But it's not. It's just picture, 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 picture. And my brain tends to kind of integrate that all together and fill in the missing pieces. So, all right, well, again, maybe I'm spending too much time here, but I really want to set the stage, because we're going to get to some harder ones. And without the foundation, the harder ones, you just get lost in why we're doing what we do. So what I've hopefully done here is I've done some geometry. I've done some geometry using the law of reflection and showed you that the image distance is inside of the mirror, so we call it a virtual image, and it's just as far as the object is in front. Now let's do the other dimension. Let's say this object has some kind of height to it. Let's say that I'm going to draw a ground, and this object is some kind of arrowhead. So it's, you know, really more kind of like this bench rod here. It's got a base and it extends upward. What I've just argued my point here is I'm looking at the light coming from the arrowhead, the top of the arrowhead. So the top of the arrowhead . is really what I'm looking at, a point. What if I did exactly the same logic for the middle of the arrowhead? Where would that be? And I hesitate to draw a bunch of rays because it's going to get so busy up there that you're going to lose the meaning behind it. But I think you know. Where would this point be? Right there. Fair enough? And if I did the same logic for the base of the arrowhead, where would that image appear to be? Right there. And then you get the idea, if I did this point by point, point by point by point, what would I eventually get is the whole image. Not just one point, but all the points. And so I would get everything that reflects in the mirror, which in this case is from about this point down. These points down all reflect in the mirror, and you see them in the same order. And in fact, you see them in the same order so that if you call this h, so there is the height of our object, and then I call this h prime, being the height of my image, then how would h compare to h prime? Yeah, so again, in the simplest case, we would say that the image has the same height as the object. No real changes there. Yeah.
So the two left arrowheads were the eyes of the observer.
Two what?
The arrows on the far
Oh yeah, so these two represent rays coming from the top of the object, the arrowhead.
The arrow on the far left and another one on the bottom.
Yeah.
Those are where the eyes are of the observer?
Yeah, so if this was the observer, this would be left eye, right eye. Okay? Now, in reality, I mean, you can see in my drawing, this makes it look like the head is huge. The reality may be that your head is only that big. And so these rays are useful in calculating where the image is, but the reality is those are not the ones that go to your eyes. The ones that go to your eye would be that one and that one. But if you trace them back, they would converge at the same point as my bigger rays. So I picked those broader ones because they were easier to calculate, not necessarily that they really were the ones that went into your eye. And so again, like this image is trying to show, is I only need two. Because the third, the fourth, the fifth, the infinite, all of them will go back to that same spot. And so I'm going to pick the two easiest ones. And that's what I would encourage you. Don't pick the hard ones to calculate where the image is. Pick the easy ones to calculate where the image is. Okay? All right. So we've done the first mirror, like I said, the flat mirror. But now, let's change that. Let's grab a mirror that looks maybe something like this. And I don't know if you can see from your distance, but see how it's curved inward, concaved inward? There's going to be a reflection. And if you look at the classroom out behind you, what do you see? Yeah, you see it upside down. And I bet you don't see the same size either. And in fact, what if I put an object close? What do you see? Is it upside down? No. And so we've got to do the rays. And where the image comes out definitely depends on where the object is. And so how this all works out mathematically all depends on a combination of where is the object, where is the image. Is the image going to be upside down or not? Sometimes yes, sometimes no. Is the image going to be behind the mirror, on the mirror, or, interesting enough, in front of the mirror? That's what I really like about this one. Here's a nice concave one. You're probably not as familiar with these concaves. You're probably not as familiar with the images being in front of the mirror. But where does this image look to you? Doesn't it look like it's out here? And it is. That's where the image is. And I think that's a little surprising. Most of us are familiar with flat mirrors. Most of us are familiar with images coming from the light behind. Most of us are familiar with virtual images. But the light could have been redirected so that it actually crossed out here and then spread out from that point. And when you trace the rays back, it would be a real image. And that's what you're seeing. That's why this ping pong ball, it's kind of fun to watch. Because as you shake its location, the image changes its location. And sometimes the image is actually closer to you than the object. And so now the fun really begins here. Let's look at what we would call spherical mirrors. A piece of mirror that is part of a sphere. What kind of images would we get from that? Would they be upside down or not upside down? Would they be bigger? Would they be smaller? Would they be the same size? And the answer is it'll be all of those, depending on where it is. So we start here with, as I said, the name, a spherical mirror. And what I mean by a spherical mirror is that it's a reflecting surface that has been cut so that there is some radius to it. And so when you physically make it, of course, it's kind of fairly easy to make. You just, take a metal rod and you move the metal rod, back and forth. It makes an arc of a circle. And it just grinds the glass, polishes it nice and smooth, and it's going to be curved a little bit. And that's how we got this one. And of course, this one was probably molded here. Some of these other ones that I'll pass around in a minute as we talked about it, here it is. I don't know if you can see it dip in here, but this is dipped in. In fact, it's dipped in this way as opposed to dipped this way, which we don't have any reflecting surface on there. So we'll give a name to this. What shape shall we call this? Again, from geometry, we will do a concave. So this is a concave mirror. It's not a flat mirror. It's curved in a way that we have a concave effect. All right? And so, let's take a quick look at this one. That's why I grabbed this box of optics here. This one you already saw last time. I'll turn it back on. This is our flat mirror. If I take a bunch of beams, I'm going to hang on to those. If I take a bunch of beams, well, maybe I'll even do the classroom lights, but you can see that each of these 5 beams come in, hit here, and reflect off. Fair enough? But I also have in here a polished piece. And I don't know if you can tell from your distance, but it's slightly curved in, not too much here. Okay? But it is part of a sphere. It is concave. And probably to be expected, what would it do? And maybe it might be better to align it this way, but I didn't want to do that at first so that you can kind of see which are the rays coming in and which are the rays going back out. But in particular, I want you to notice that magical point right there. Okay, if I put it off to the side, you'll see it, right? That magical point. What are happening to these 5 rays? Yeah, they all converge right there. Okay, and we're going to refer to that as the focal point of this mirror. it is designed in such a way that it will make all the beams of light go to the same point. Now here's where I'm going to skip a little geometry so we can get to, I think, more important geometry here. But if I were to draw this, and I will draw kind of this dotted line down the middle, and I'll refer to this as the optical axis of it. If I were to draw array, how many do I have here? 5? Array, and array. The easiest one, I think, to see is this one. What happens to this ray as it comes in and it hits the mirror? Yeah, again, this is the law of reflection. At this, the incident angle is 0. So it will reflect back off at 0. That is that middle ray right there. It goes straight in and goes straight back onto itself. If I turn the mirror just a little bit, and maybe even dim the lights a little bit, you can actually see that ray coming back. But I want to put it right there. So again, that's probably the easiest one to draw. The other ones go where? Well, how about the one a little bit above, and for that matter, the one a little bit below? I think you can see from the symmetry above and below, they're essentially going to do the same thing, just reversed. What's going to happen to, say, this one? Yeah, and I'm hoping you are seeing that if I draw the normal, where would the normal go? In fact, maybe, yeah, I got it dotted line there. Where would the normal go as opposed to the ray? Good. The normal is back to the center of curvature, right? Maybe I could call that point C for the center. Is that where the ray would go? No, why not? Right, the law of reflection would say, well, this is coming in at some angle theta. So when it comes back, it's got to reflect at an angle theta. And so this top ray goes back to some point. As hopefully you see in the demonstration here, all the rays are going to go back to that point. But I want to emphasize, that point is not the center of curvature. In fact, let's put a little f here to represent that point. That's going to be what we'll call the focal point. That's the point, whereas if you start with light coming in parallel, when it hits this curved mirror, it goes back to that point. Now, not a surprise, I think you can see the same geometry in the ray underneath it. That would come back to here. And the normal would be from the center into the mirror. Here's the part that I said, it's probably not so obvious, but it is approximately true, not 100% true. If this mirror is curved, not too much, and I would argue this is probably curved too much. It's probably why the images in here look a little blurry. They don't exactly work out. Whereas this is curved enough that it's probably get some images that aren't so blurry. But if I were to draw that ray, again, I would draw the normal. And of course, here's what I want you to see. That angle would end up being twice that angle if these are equally spaced. My drawing doesn't show it as equally spaced as the little equipment I have here. But that angle then turns out to be approximately twice as much, which makes this, actually maybe I shouldn't even say twice as much. I'll just say a new angle 2. But the reflected angle is also a new angle, theta 2. And what I really want you to see is that that incident angle then is going to be a little bit bigger than that incident angle. Even though the rays are going in the same direction, the difference is it has curved. And so that means it's going to curve down more, which means it ends up going at the same spot. It's twice as high, but has twice the angle. And it ends up going at the same spot. So does this one. And so all 5 of these rays then meet at this point called the focal point. And as I said, wanted to convince you that it is not the center of the circle. And so here's what we will do.
It's not, it might look like it's a double relationship, but it's not. It's sort of arbitrary and related to the curvature.
It would be related to the curvature. And so if the curvature is not much, it would be twice the angle. Okay? Because...
We're going to be assuming that, I mean, are we...
Okay, yes. So here's what I want to emphasize. So here's what we're going to do. We're going to make our geometry a little bit easier. Okay? And then depending on where your education takes you into the future. But for us, just to get started, and for these 4 chapters, or I guess we got 3 left, of optics, we will just say the curvature is small. Small enough that this is twice the angle of that one, which also means that the curvature is not much, so that this point and this point, left and right, are approximately the same, not exactly the same. This would be a much harder geometric problem, okay? But if they're approximately straight up and down, then I can call this distance the focal length. And so again, notice I'm measuring distances, right? Notice I'm measuring it from what? The mirror to that point. Everything is measured from the mirror. I've erased it, but remember our flat mirror. How did we measure the object distance? Object to the mirror. What was image distance? Image to the mirror. What is focal length now? Focal point to the mirror. Everything is to the mirror. How far from the mirror? And because we're going to make an approximation and say that there's not much curvature to it, we won't really distinguish that distance versus that distance versus that distance. It's just one distance and one focal length. If you really wanted to make a clear image, you would have to be a little more sophisticated than what we're about to do. But this is a good first step. Yeah.
Is there some sort of relationship between the focal length and the center?
Good. And the reason we want to take this very simple relationship, if that's twice the angle, then, and that's the same distance, then we can do tangent, and that distance here has to be half of that distance. And so again, I wouldn't call this a proof because I want to do some other proofs, but I want to get to the answer that the focal length, as again you're noticing from the geometry, would be half the radius. And so, no, I want to prove some other things. Your author has it pretty well. But again, because it has some approximations, well, maybe I will a little bit later when I do a, well, shoot, I'll just do it now. What the heck? But again, you have, if this is the height of the first one, call it x. Then this is the height of the second one, twice x. So then, if I draw a line out to here, and a line out to here, I would have tangent of theta 1 would be x over the radius, and tangent of theta 2 is going to be 2x over the radius. Theta 2, thank you. Theta 2. I want to show it's twice theta 1 here in a second. But this tangent, and maybe I should have waited, because here's what I wanted to show you. What does a tangent function look like? Doesn't a tangent function look like that? And for small angles, Isn't it kind of just a straight line, kind of in the middle? And that's my approximation. I know the function actually curves a little bit, but the function itself is approximately a straight line for small angles. We did the same thing back when we did the pendulum. Remember we did the pendulum? And when we did the pendulum, we had sine theta. And what did we say sine theta was roughly equal to for small angles? Yeah, we said it's roughly equal to theta because we took a theta function or a tangent function and we said it could be roughly a straight line. Anything you can kind of approximate as, you know, the tangent at that point. So the derivative would be that slope. So the derivative of a sine is a cosine. And the cosine at 0 is 1. And so we had a line of slope 1. Well, the same thing here. What's the derivative of tangent? Secant squared. What's the secant at 0? 1. And 1 squared is 1. So I would say, just like sine theta is approximately equal to theta, tangent theta is approximately equal to theta for small angles, for the same kind of mathematics. And so I can write theta 1 is roughly x over r, and theta 2 is roughly twice x over r, and therefore theta 2 is roughly twice theta 1. And then, doing the same geometry here, I would get that distance twice that distance. And I better make sure I get to some more math here. I mean, some more of our physics. Okay. And so don't be surprised if we do a lot of this throughout the rest of this chapter. You will see the author do it. You will see me do it. Every time I see a sine theta, I will say, you know what, that is roughly theta, at least for small angles. And if you remember when we did the pendulum at the beginning of this semester, sine theta equal to theta worked out for almost 30 degrees. That was a 0.5 radians. In fact, I'll grab my calculator again. Oh no, I didn't bring it today here. But if you go sine of 0.5, and make sure your calculator's in radians, you will get like 0.48. And so the sine of the angle is really close to the angle. And the tangent is too. And that's essentially what this proof involves there. Okay? In fact, maybe at this point in your education, it's time for me to use a fancier word. Maybe what I should do is take the sine of the angle and expand it with a Taylor series. And I won't have the time to go through all the derivatives. But you can begin to see that for small angles, again, let's say a half, a radian, you take a half and you cube it, what do you get? An eighth. You then divide it by 3 factorial, which is 6, you get 1/48. That's roughly 2%. So this number is 2% of that one. So if you're willing to take a 2% error, then just throw those away. So sine theta equals theta. So Taylor series are really nice functions, and that's really why I brought it up, is because you may be, you know, in your math right now learning all these wonderful Taylor series and always asking yourself, why do I care about these? Well, here's the answer. What if you didn't want to make a small angle approximation? What if you wanted to make a better camera with a better lens? You wouldn't just say sine theta equals theta as we are doing today, and tomorrow, and the next day, and for the next 3 weeks. But you would take the next term. You would take that next term. And if you weren't happy with the image you got there, you would take the next term, and then the next term, and then the next term, and then the next term. And you can do this, you know, as far as you want to get as much accuracy as you want. It's just a matter of how much programming time you want the computer to do to process the information. And so you can make your image better and better. And then, of course, your lens would become better and better. And, of course, it'd be more expensive and more expensive. So you can get a cheap lens or a good lens. Or, in this case, a mirror. A cheap mirror or a good mirror. But I think you're seeing the idea here. But what I wanted to point out here in this first thing is that when you have a mirror that is shaped like this, concave, when it's part of a sphere, what will happen is any of the rays that are parallel go back to this magical point called its focal point. Now, why do I care about that? Well, because again, I want to do the same thing that we just did for this flat mirror. I want to put an object in front of it and ask you, where is the image? How big is the image? And we can do that by tracing the rays. We could do that by doing the same geometry that we did for the flat mirror, except harder geometry. We won't get congruent triangles, but we will get similar triangles, and so let's give it a shot. So our first non-flat mirror would look something like this. I'm going to take this curve. I'm going to draw what I'll call here the optical axis. To give us some kind of reference, I'll even put a C for the center of the mirror and then an F for the focal point of that mirror. And so those are my two magical points that I'm going to keep my attention geared on. I'm going to start then by saying, what would happen if I had an object out here? And the same as before, let's just start with a single point, and then we'll give a size to it. But if I start with a single point out here, and I'll say, all right, what's going to happen to the light as it comes into this mirror? And fortunately, let me not try to draw all of them, but only two of them. And there's three of them that are pretty obvious where they go. Maybe you'd even say four. But I only need two. I'm going to pick the two easiest ones. I'll start with what I think is the easiest one. What is the ray that comes in like this? The ray that is parallel to the optical axis. The one we just drew here. Where's it going to go? It would bounce off the mirror and go through the focal point. That was just our 10-minute discussion of, okay, what happens to light when it hits a concave mirror like this? But we need two. Anybody see the second one? The reverse, exactly. If the one that goes parallel comes off and goes through the focal point, and since the angle of incidence equals the angle of reflection, the logic should hold identical to a ray in reverse. And here's what I mean by reverse. A ray that is coming in and going through the focal point would hit the mirror and go parallel. And so this ray would look like that. And I think those are the two easiest ones to draw. Like I said, we probably could draw a couple of more. Let me not put them on the board here. I will just mention them. My drawing's not as clever as it should be, or as proportional as it should be. But the one that goes through the center should hit the mirror and go straight back. So it should go through that point also. So I'll cheat. Right? And so that would be a third one if you wanted to draw that one. But again, I don't. I think these are the two easiest ones. Another one that's not too bad to draw is the one that comes out and hits right at this point, because then it's essentially a flat mirror, so then it comes straight out like this. But again, notice it would go through that point. In fact, all rays would go through that point. And that's really what I want you to see. So where's the image here? Isn't this then the image? Because the image would be the interpretation of an observer over here, right? This ray goes to one eye. This ray goes to the other eye. You would trace it back as if, where's the light coming from? Right there. And notice something different than we saw before. One is size. Let me skip that one for a moment. But did you notice it's in front of the mirror? The light really did come here. And as a result of that, That's what I was saying earlier, that we want to make a distinction between a virtual image, where the light appears to be coming from. So in other words, when the light appears to be coming from inside of the mirror, we will call that a virtual image. But when the light actually converges in front of the mirror and then diverges out from that point, the light really did meet at this point. So not only is it an image, but since the light is really there, we'll call it a real image.
You actually touch it pretty well.
Another way of saying that is, yeah, if you put your hand here, it would get warm, right? The light really is there. Whereas the virtual one, if I put my hand here, it doesn't get warm. Those are the kind of images you see in magic shows where the magician puts his hand in the flame, you know, and he's projected a virtual image there and putting his hand where the light really isn't. The flame is over there, reflected off of a mirror, puts his hand over there, and of course the hand looks like it's in the same spot, but it doesn't get hot. So, all right, well, but it does. But the real image, particularly, is interesting to me because I don't think it's as common. It is out in front of the mirror. It is closer to you. That's why I did this one to grab your attention at the beginning. Was I'm not sure too many people have seen this. But can you now tell that the image is actually in front of the mirror? And sometimes the image is actually in front of the ball. And I'll pass this one around in a second, but there's some other things I want to show you before I do. I'll do this one here. This one kind of shows the same thing, but it's kind of fun to play with. If I kind of take it apart here, you will see the concave mirror down here. And down here, you will see the object. It's a start button. Nothing real fancy. We used to have a quarter, but it disappeared, so you know, we got a start button there. But if I put the start button down here, and I put the lid on it, the light will reflect off here. And it actually does two mirrors, so we got more to talk about before I fully can explain this, but it's got another mirror up there. But it will form a real image right there. Now you can't see it until you're looking over it like I am, but the light will come out of here. And if I stand here, and this is why I'll pass it around, if you hold it, not too far, not too close, because if you just look straight down, you just see the start button, okay? But if you hold it so you're kind of looking in here, and it looks like the got moved a little bit. So as you guys pass it around, it may move, okay? But it says start, and I just want to push it. And since all light would follow the same pattern, this really gives it a realistic look. You shine the flashlight on it, and you might think, well, there's really not an object there, so the light's not going to bounce off of it, right? But what it does do is go inside, bounce off the mirror, bounce off the real object, and come back out as if it was bouncing off of the object. And so it has the appearance of there's something really there. And so again, let you guys play with it as you pass it around there. And remember, as you pass it, try not to tilt it. It will slide, and if it gets to you, just make sure it's right in the center. Look down the middle, make sure it's right in the center. It's got to be positioned just right. And then you'll see the image really, really well. Yeah.
Why can't they do that with TVs yet?
I wouldn't say it can't be done. I guess part of the question is, why isn't it being done? And I think it's more about a cost issue. I mean, a good example is of real images, and I think why this, I don't know if it really scares anybody, but have you ever been to Disneyland's Haunted Mansion? Those little ghosts going around the room?
The ones that try to get out of you.
Yeah. Those are projected as real images. And so there's one part on the ride where you are riding above a, well, I guess it's a ballroom. And then the ghosts are dancing. Now there's tables, and they're just dancing right through the middle of these tables, right? And it really looks like there's objects there. I mean, those ghosts look like real ghosts. I mean, they go right through the table. They just circle around. And if you understand how it's done, is the reason you're up on a platform is because underneath you are small images of ghosts that are really dancing around with a bright light and a mirror. And so you are looking into as a mirror. And they have projected the objects into the mirror, formed a real image out in the center of that dining room, and then it goes to you. And so that's where the light appears to come from. And they magnify it. This one, as somebody already pointed out, looks like my image is going to be smaller, and it is. But there's also ways of getting real images and making it bigger. We'll do that one next here. But that's what they've done at the Haunted Mansion, and it looks like something's really out there in the room. And it's as much as three-dimensional effect. But of course, in that case, they've got real carved images. You wouldn't do that on a TV monitor. So.
There's no way to do it.
No, I wouldn't say there is no way of doing it, because you can get the equivalent of a real image with a hologram. So you can make a hologram and then put the hologram through the concave mirror and then project it. But between expense and space, I guess, is the answers. Yeah. But you can get it closer and closer if you're willing to put in the expense. And again, you're from the Air Force. I don't know if you did any, but some of those simulators where they train the pilots on are very realistic, because they really put in the money and the technology to make it look like you are in a real cockpit as you're training. Yeah. And arcade games too, but not to the level that they do in real simulators at all. Okay, so good. I'm hoping you're seeing a bunch of things here, and I guess I better keep going here kind of quickly. I want to make sure we cover all of our mirrors so we can do lenses next time here. But this, what do I do with that red pen? But this one, as you pointed out, and why it looks so neat, is you've got an image out in front of the mirror. Now, this is where that image is. Let me do the same notation. Maybe I'll save the blue and the black to make triangles, okay? But let's do the same notation. Let's call this P. Same as we did before. What's the meaning of P? The distance that the object is from the mirror. So, what will Q be? The distance that the image is from the mirror. So same notation, P and Q, okay? But again, as we went through this geometry, hopefully you realize that's why that is the image. And in fact, let's do the same thing we did for the mirror. If I change this object to not just be a point, but this to be the top of an arrowhead, and so again, kind of back to this bench rod here, and I did the same logic, and let me do the base of the arrowhead. That might be easier to see in this case. Where's the base of the arrowhead going to be formed? Well, light coming in right along that optical axis is going to go straight back, right? And so the base is going to be right there. Where's the middle of the arrowhead going to get formed? And again, let me not draw too many rays, otherwise I think I'll make things worse. But that is what I would get if I drew a ray through the focal point. It would hit here, and when it goes parallel, it'll go right there. And so what I will get is I will get an image, and notice it's upside down.
That image curved?
No, not in our simple approximation where these are essentially the same distance. If they are not, if you take that next level, which like I said, we won't this semester, but some of you probably will if you go into optical engineering here, and then it would be a little curved. Yeah, wouldn't be exactly a plane. But again, isn't that what you saw earlier? That's what this mirror was for. Don't you see? Say you look at the back of the room in here. Is it upside down? And is it smaller? Yeah. And that's what I wanted you to see here. Now, that's not the only case we can get. In fact, this mirror can do three things. It can make it upside down smaller, upside down bigger, and right side up bigger. It can't make it right side up smaller. That one will. And so this will be our fourth possibility. So between making things bigger and smaller and upside down and erect, those are our 4 combinations. That's why I call this one the interesting mirror, because it does 3. So I call this one kind of the boring mirror. It does one thing. Makes things smaller, right side up. That's it. Now, not to say it's not useful, that's all it ever does. And that's what I want to get across to you before the day's over. The 4 combinations that we can have. Plus, you might say the 5th combination. This mirror only does one thing, but this one can do 4 things. And this is a picture of it being upside down and smaller. Let's put in some more symbols here. Remember, this was the height. So we'll still call this height, H, height of object. This would then be H prime, height of image. So let's do some geometry. Just like we did for the flat mirror, but a little bit harder because our triangles aren't congruent, but they are similar. Let's look at a set of triangles. Let me draw them in black. Many of you might remember this same set of triangles we did in 102. We drew a set of triangles. And so here is this black triangle. I think this pin's a little bit better. And take a close look at those 2 triangles. I claim they're similar. Congruent? No. Similar? Yes. Because that angle's the same as that angle, and here, roughly, I'm drawing a 90 degree. That's my approximation. And here, I am drawing a 90 degrees. So I would say 2 of those angles are the same, which makes the third angles the same, which makes them similar. And then, if I realize that this over here is the height of the image, and sticking to my color code here, I'll do this in black. If I write height of image is to height of object, I'm saying this side of the triangle is to this side of the triangle as this, so that's focal length, is to this. And how would I represent this? Yeah, P minus F. P minus F. And so the ratio of their heights, which, by the way, what should I call the ratio of the heights? Magnification, right? How big is the image compared to the object? And in this case, should be less than 1, right? In fact, I'll even go you one better. I'm going to call up, and this is why I really wanted the overhead the whole time here, Table 1 in your book, because I think probably the most challenging part of optics is this. It's not so much all of these rays, because what you will see within the next, hopefully, 35 minutes is we'll get some nice set of formulas that in all 5 cases that I showed you, it's really the same set of formulas. Whew. If we're willing to use pluses and minuses with some of our symbols. So the good news coming up here is we don't have to learn 5 different scenarios. And then we have lenses with another 5 scenarios. We don't have to learn all 10 scenarios. We just got one set of equations that work for all 10 cases. That's the good news. But the bad news is to make those equations work, we have to use pluses and minuses appropriately. And that's why your author has given you a couple of tables. Look carefully at this. Magnification. Height of image. It's positive when image is upright. What if the image is inverted? What am I going to say? Negative, right? So, as you will hopefully see here before the day's done, is we will have a plus and minus for P, a plus and minus for Q, a plus and minus for H, a plus and minus for F, and a plus and minus for the magnification. So we've got a certain set of rules that if we stick by will be very worth it to you, but it's gonna drive you crazy, I'm sure. Takes a little while to learn the rules. So I'm starting off by saying, look at this table, learn the table, memorize the table, and so we begin now. Because I have done something here that doesn't really fit the rules. And I want to make sure I fit the rules. Because when I fit the rules, all 5 scenarios come out to be the same. And you will appreciate that. What have I done wrong here? I have treated everything as positive numbers, right? When we do geometry, and we say the height of this is to the height of this, and this to this to this to this, we treat them all as positive numbers. And that's fine, because I really do have a positive number here, a positive number here, a positive number here, and a positive number here, but I don't have a positive number there. H prime is there. So let me just do something here real quick. Why don't I just do this for a second? Here's what I'm really saying here. What I'm saying is the absolute value of the magnification. Okay? And so really this magnification is a negative number. What does negative number mean? Image is inverted. Okay, this is going to flip it over. And of course that's what you see in the picture here. And so I have the magnification is equal to this ratio. Now, let me try another set of triangles here. Here, in the blue, will be another set. From here, up to here, down to here, across to here. And I hope you'll see by the same logic, those 2 blue ones are similar, aren't they? These 2 angles would be the same. They're each 90-degree or right angle triangles. So 2 of the 3, therefore the 3 are the same. If I project this across, this is supposed to be the height of the object, so that's an H. And if I do the same logic here with the blue triangles, if I write H prime is to H, absolute value, okay, because I'm just going to worry about absolute numbers here for a second. But H prime is to H, so the height of this one is to the height of this one as this length. How do I represent this length? P minus F, exactly. So P minus F is to Q. Thank you. Q. We got image, Q. Oh, good. You guys already got it figured out. So Q minus F gives me that. And then what's this one? An F. Okay? So that's really my geometry. Let me put the negative in here for just a second. If I continue on, and I'll put it over here on this part because I want you to see then all 5 scenarios that I come out with are actually going to be the same thing if we follow these rules. And so again, one of the first rules we are seeing is that you don't always have positive numbers. I have treated them all as positive numbers. There are some times we want to treat them as negative, and we're seeing it for the first time here in the height of the image. And again, that will be helpful, because if you ever come up with the height of the image as negative, it means, yeah, it is the, and I was going to say upside down, but I probably should say it's opposite of the object, because the object could have started upside down and then turned it back over. But it inverts it. Okay? And so as I write these 2 equations over here, I will write it as H prime is to H. So in other words, I'll get rid of the absolute value. That means I have to take the negative of this, right? And so let me write it as F over F minus P. Isn't that the negative of that one? So when I get rid of the absolute values, I take the negative of that one. Same thing here. If I take my second equation, which is H prime is to H, I take the negative of it, I get F minus Q over F. Okay? Did I do that right? Yeah. Okay. So those are the 2 equations for this case. Now I want to convince you it's really the same case that we got back here with the flat mirror. What was the focal length for the flat mirror? Yeah, maybe I should start with what's the radius of curvature of a flat mirror? Infinity, right? It's not 0, right? When something looks flat like the Earth, it's because it has a big radius, right? And so big radius, infinite, means the focal length is infinite. All right, so take the limit as the focal length goes to infinity. What do you get? 1. What do we say about a flat mirror? How does the height of the image compare to the height of the object? 1. Well, they're 1, right? They're both positive. You get 1. Same thing down here. Yeah, it does work. Right? In fact, let me keep going with the math here. Let's put these two equations together. If I set that equation equal to that equation, what do I get? So if I say f over f minus p is equal to f minus q over f, and I go through some arithmetic here, or maybe I shouldn't say arithmetic, algebra, I'll do cross multiplication. That's f squared, the extremes. The means become f times f, that's f squared. Then it becomes minus fp, then it becomes minus fq, then it becomes plus pq. And both sides then have an f squared in them. So they can go away. In fact, let me take these negative ones and move it over to here and even factor out an f. So this becomes p plus q, and this is just the product of pq. And I'm going to simplify this, or it kind of depends on your definition of simplifying. Because we don't usually do this as an algebra class, but it will be very helpful for us to see it and memorize it this way. I am going to move the f to this side and the p's and q's to the other side. Now why? Because I think this simplifies. And again, it depends on your definition of simplify. But if you had 1 over 4, and maybe I should call it 1 over a plus 1 over b, what would you do to add those together? You'd get a common denominator, a plus b, and then you would go b plus a, right? Isn't that what I have? And so I claim that this is 1 over p plus 1 over q. And this, then, is the mathematical relationship that you need to commit to memory. It will be useful for all 10 cases we will cover in this chapter. The only catch to use it is to remember when to use positive and negatives. Okay? And so I have shown you 2 of the 5 that I want you to see today. This is those 2 put together. And so maybe I will put it right underneath it. 1 over f equals 1 over p plus 1 over q. Very important relationship. Yeah?
Doesn't it matter that for the first formulas we use negative h prime?
Well, okay.
So it flips f minus p.
No, well, if I had set these equal and did the algebra, I'd get the same thing. Because I would have it would be the same as having a negative and a negative compared to what I did do. So yeah, no, so it come out the same thing. But I don't want to spend too much time doing absolute values because that will lead you down the wrong road. I want us to use pluses and minuses. I'm just trying to connect it to your geometry here as we kind of get the ball rolling here for our 10 cases we're going to look at here. This being our second one. In fact, let me go one step further here. Another way of putting these together would be to continue with this relationship. Watch this one here. Let me continue with this one. This says h prime is to h as f is to f minus p. Let me just multiply top and bottom by 1 over f. Watch what happens. F times 1 over f is 1. But f minus p times 1 over f becomes 1 minus p over f. Fair enough? So let me put the 1 minus, and this is kind of nice here. Do you see it here with this equation? How can I get a p over f? If I multiply this equation by a p on both sides, wouldn't this side be p over f? And so what would this side become? 1 plus p over q. And so it simplifies to q minus q over P, right? And so the second equation that, again, you want to commit here to memory or go back and derive from geometry, I don't care, is that. Because I claim, again, that every scenario we are going to look at will come out to be these two equations if we're willing to use some signs, pluses and minuses. And so, like I said, that might be the hardest part of this chapter, remembering when to use the pluses and the minuses. So far, I've only shown you the H and the magnification. But there are other options coming up here real soon here, if we get that far here today. But I wanted to write these on the side of the board here, because as I switch it up here and say, let's look at a slightly different picture now. Let me erase this and come back and put focal point here, center of curvature here, and now let me put my object a little closer. Because I'm hoping you can see then that if my object was always beyond the center of curvature, the rays I drew would be exactly the same. Now, granted, the numbers would be different, so the magnification may change, and the position of the images may change, but they would always be kind of the same relationship. They would always be really far out. So now, what would happen to these rays if I was a little bit closer in? Draw them now. What will you get? And fortunately, it's not much different. In fact, this one I don't think it's any different. Let's see what we get here. Let's draw the first ray. If I draw the ray that goes parallel, where does it go? Through the focal point, right? What's the second ray? Through the focal point and then parallel. So again, looking at this picture, where would you say the image is? Here. So again, it is a real image. It would be upside down. And the only thing really different between this picture and the last one is what? It's bigger. It's closer to you. And because of that, it's sometimes harder to see. And so in a minute, I'm going to pass around some of these ones so you can kind of look at it yourself. But here's what I'd like you to do. When you get your own concave one, look at something far away. Like if I look at that board over there. Where is that board? Ah, there it is. I see that bulletin board, and it's upside down, and it's small. I can't even read the words, right? But on the other hand, if I get it a little, well, I'd have to get real close to it. I'll use my eye. So if I look at my eye, okay, it's upside down and small. And as I get closer, it's getting bigger and bigger. Ooh, and right about there, it looks like it's about the same size as my eye. And so as I get a little bit closer, it's actually a little bit bigger. It's also getting so close that it's hard for my eyes to focus on it, so it's maybe not a good option there, but it looks bigger here. And so this is the scenario I would get under here. Now again, if we do the same thing, if we do our same notation, where we call this a P, we call this a Q, we've already called that an F. If we draw a black triangle, and well, I guess I lost my color coding here, but my black triangle was the one that included this, where this is the H prime and this is the H. And if I come over here and look carefully at these two triangles, what changes here? And again, let's just do absolute value for a second. H prime is to H as F is to P minus F. Nothing changed there. So same equation. Let's do a set of blue triangles. The set of blue triangles was this one. And again, if we kind of give the size of the object over here so we can see it, and we look at these two triangles, calling this H prime, we would again have H prime is to H, so H prime is to H as this distance. Well, that distance would still be Q minus F, and this distance would still be F. And so don't I have the same equation? So I'm hoping that I can save some time. Do you want me to go through all this algebra again? I mean, what am I going to get? If I start with these same equations, what will I get? Exactly the same equations, right? So there's my proof to you that this set of circumstances will still give me the same equation, except, what do you notice about the image and the object? It's kind of as if they reversed roles, right? See, the last picture I had, and maybe I'll draw the last picture over here. So if this is the focal length, this is the center. The object was outside of the center of curvature, and the image was formed between the two, right? And so the only thing that has really changed is that now that the object is between the focal length and the center of curvature, the image is now out here. So it's kind of like these two reversed roles. But you can see that in the math. If you exchange P and Q, don't you really get the same equation? And so the positions don't surprise you, right? Now, you wouldn't get the same magnification. You should get the reciprocal of the magnifications if you interchange P and Q in the math and in this picture. And so again, here's how I like to think about it. As I'm trying to say, this equation has worked for the three cases I have now shown you. It had worked for the flat mirror. It had worked for the object outside of the center of curvature. It is now working for the object between them. And for me to keep it straight in my mind, I remember that these are really kind of the one and the same. One will be formed between the two. The other one will be outside. The one on the outside is always bigger. The one on the inside is always smaller. They're always inverted from each other. That's what this math is saying. It doesn't matter if you interchange P and Q. The positions are the same. And when you interchange P and Q, you get the reciprocal. And so this scenario is how you would get something upside down and bigger. This scenario is how you would get something upside down and smaller. And again, I don't know if I can hold this carefully enough that you can see it. But if you look at something far away, like the back of the room, you will see it upside down and smaller. If I hold it a little bit closer, but not too close, because if I go too close, it's not upside down anymore. Is that too close? That's probably too close. Oh, maybe I'm too high. Yes? No? I'm going to give up with this one. All right, so I'm going to go to this one. That's what was neat about the ping pong ball. This was deliberately built to be a hemisphere, half of a sphere. Where's the center of curvature?
Center?
Right there, right straight up and down. So when you take the ping pong ball and you hold it straight up and down, so it's at its center, looking at this math or looking at this picture, where would the image be formed? If P is twice the focal length, what does Q have to come out to be?
2F.
Twice the focal length also, right? Because 1 over 2F plus 1 over 2F is 1 over F. And so the case I'm looking at, and why this was set up the way it is the scenario where if this is the focal length and this is the center of curvature, if you put something right at the center of curvature, where's the image? Center of curvature, of course it is also inverted. How big is it? Same size. Upside down. But when P and Q are the same number, you get the same size. That's why this works kind of neat. Because when you hold the ping pong ball, and the reason we chose a ping pong ball is when you invert a ping pong ball, guess what it looks like? A ping pong ball. So you can't really tell in this setup that it's inverting. But when you look at the image, it will hopefully look roughly the same size, doesn't it? Until I start shaking it. And what happens when the ping pong ball is out here? The image is inside and smaller. When the ping pong ball rocks to the inside, then the image is outside and bigger. And so as this thing rocks a little bit, you will probably see the ping pong ball rock and keep the same size. The real object doesn't change. But as you focus on the image, can you see its size change? And you can't see it go upside down. But if I exchange the ping pong ball for a pin, you will hopefully see, and it's hard for everyone to see, can you kind of see it goes upside down, depending on where it is? And so in the few minutes we have left, I'll let you play with it here and kind of look at it and say, where is the image? Yeah.
What if your object is around the focal point?
What if it's right on the focal point? Oh, let's go, well, let's answer that after we go inside the focal point and then right at the focal point. Because what we're going to see, there's a transition that takes place, and at the focal point, I'll just give you the answers. The mirror won't be able to focus it, and so it'll just look blurry. In fact, since we're getting pretty close to running out of time, and so this can all get passed around, I'll pass around these too. I'll start one on this side of the room and the other one over here on this side of the room. But as I said, if you take these for a while and you can study them, and we have them in lab too, so you're going to play with them in the lab. But again, looking at something far away, like my eye, it is upside down and smaller. Now it's upside down and bigger. And the third scenario is, what if I'm real close? And what we're going to see is the third combination, which I think you guys can see as a group when I do this. When I put an object real close to it, what do you see? Bigger and right side up. And so this is our third scenario. And so what would that one look like? And this one is significantly different than the other two. And so let's try number 4 here. And so, if I take all this mirror stuff here, and I say, okay, let's take the mirror, focal length, center of curvature. Now, let's put the object in the third possibility. So notice how it's divided into 3. Those are the 3 combinations we could have. Let's draw the rays. Let's do the geometry. Let me convince you that it'll still be these equations. Yes! Okay? And so many of you who might remember from 102 is we never got this far in 102. We left you with forcing you to do the geometry so you would be more equipped to come now. But the good news is you don't have to do the geometry every time. The good news I'm trying to say is these 2 will work for all 5 combinations. Flat mirror, the 3 combinations of the concave, and the 1 combination of the convex. It will all work as long as you're willing to use pluses and minuses. So learn the pluses and minuses, and then you don't have to worry too much about where it is. You can just go through the math, and then if you come up with a negative or a positive number, it tells you some information. So at first it seemed like it was a pain that we have to use the pluses and minuses, and then we realized that we can just go and do our algebra. This is one of those few cases where you can just blindly plug and chug and do better than okay. You will get the answer, and you will get a negative sign or a positive sign, and it will have a meaning to you. And so plug it in. Plug and chug and come up with the answer. So as I draw this ray, what would happen to the ray that goes parallel? Yeah, again, it's going to go through this focal point right there. This is probably the harder one to draw. What about the second ray?
The ray came from the focus.
Good. I don't want to draw the one that goes through the focal point because it never hits the mirror. But what I can do is draw the ray that is coming from the same angle and direction as if it came through the focal point. So that's an important phrase, as if. It didn't really go through the focal point, because that would go the wrong direction. But since it's closer in, as if it came from. Because when that one hit the mirror, what would it do? Yeah, wouldn't it go off and go parallel? So now, our observer over here would see what? Where would our observer say the light is coming from? Yeah, and so we're back to a virtual image, like we saw with the flat mirror. Here's our image. Our image is behind the mirror now. And again, since the light doesn't really come from behind the mirror, it's just having the appearance of coming from behind the mirror, we're going to call this a virtual image. But again, if we use the same notation and the same triangles that we looked at before, I would call this the P. How far is the object from the mirror? I would then call this the Q. How far is the image from the mirror? And if I look at a triangle, let me do a black triangle first. I will look at, say, this big black triangle together with another black triangle that's kind of embedded on top of the big one. And in fact, since those lay right on top of each other, I think they're harder even to see that there's two triangles there, but it's easier to see that they're similar. But if I look at those black triangles and I write out the equation, I won't get that same equation, but I don't have to worry about absolute values. So watch what happens, and now you'll see the advantage of not worrying about the negative or calling upside down negative. If you draw this, this would be the height of the object, and this would be the height of the image. And so when I write height of the image is to the height of the object, according to what we had talked about earlier, these are both positive numbers, so I don't need to put absolute values there anymore. And so when I look at this black triangle, I would say the height of the image is to the height of the object as this distance. What would you call this distance? Focal length plus Q, right? Focal length plus Q. Now, let's be careful here. You really mean absolute value there, don't you? Because now maybe you'll see the reason for this rule, image. When do we call the image positive? Well, when it's in front of the mirror, and that's what it's been up to this point. But where is it now? It's really behind the mirror. And so now my image is a positive number because it's upright, but my image position I'm going to treat as a negative number. Because when I do that, this is really what I mean, right? The absolute value. Of course, I would also divide it by the focal point. And the reason for that, if I treat that as a negative number, that's really what it means, right? It really means minus a negative number. Well, I'm hoping that equation looks just like this one. That's the advantage of calling Q a negative number here now. It will make it look like that equation, which is going to make this the solution, as long as the other one looks like that. So let's try the other triangle. So the other triangles would be this. I will draw up to here and down to here and across to there. Now again, I've drawn my picture with a lot of curvature, so maybe this would be better drawn like that, so you could see it. But this would be the height of the image. So my blue triangle would look like this. Height of the image is to the height of the object as this distance, that's focal length, is to this distance. And how would you get that distance? Well, I guess it would be focal length minus P. So focal length minus P. And again, I don't need to put absolute values because that's how we treat positive numbers, right? We were saying the object is positive when it's in front of the mirror. We were saying the focal length is positive when it's concave. Okay, so that's how we got started with our signs here. But isn't that equation the same as this one? So again, let me say algebra by saying, if I draw those rays and I get this relationship, isn't it going to come out to be these? And so there's our fourth combination, right? Same equation. So I want to emphasize, this equation has worked for all 4 cases. And hopefully, probably not the 5th one today. But we will use that same equation. The thing I need to remember, though, is when am I going to use an image that is positive? And when am I going to use an image position that is negative? When am I going to use an image height that is positive and an image height when it is negative? If I stick to these rules, then that set of equations will work for all 10 cases we're going to talk about in this chapter. And you've seen 4 of them. They actually work out really, really nice. Now I want to point out here that this one here has made it bigger. And so there is our 4th combination. And opposed to trying to rush the last one, which I'll do it on Thursday, what is the last combination?
On the focus?
When it's on the focal point.
Okay, the last combination is this mirror. Okay, and so let's see. Running through these, that mirror made things exactly the same size. And the image distance was the same as the object distance. Fair enough? This mirror did what? 3 combinations. Upside down and smaller when the object is really far away. Upside down and bigger when the object is between the focal length and the center of curvature. And now the last combination of this mirror is what?
When it's really close.
When it is close, you get right side up and bigger. So we'll run out of time to work it out, but I wanted to put these all together. So what's this one going to come out to be? Can you see it? What do you see? Smaller and right side up, right? That's our 4th combination. So I'll wrap up today with asking then, what would be the usefulness of this? What would this be used for? What good is this? Okay, so the light comes together, as you said, frying things here. Okay, fair enough. I was looking more at the images that they form, though. But isn't this making things bigger? You can either flip them over and make them bigger, or leave them right side up and bigger, right? And so things that are close will work that way. And I point that out because I think many of you ladies are familiar with this mirror. Where do you see this kind of mirror? Right, these are those cosmetic mirrors, right? That you hold and you put. I know my wife has one, and it's like you can see all the details there, right? And on hers, it's got different lights on it, so it's got daylight, night light, fluorescent lights, and you put on the light, but it definitely magnifies it. How about this one? Where do you see this one? Okay, one thing is notice the broad angle it gets. Because the light comes in from the far side and goes this way, you can get a wide angle. And so people have said like security, blind spots, true. So give me 2 places. Car mirror is a really good one, right? And I'll fit that together with convenience stores. They'll have them in convenience stores for securities. I've seen them in hospitals for blind corners. What'd you guys say? Oh, but the car mirror is the one I wanted to point out. Have you ever looked in your passenger side mirror? Objects are closer than they appear. Why does it say that? Because this is making it smaller. And one other place where you won't see the writing, objects are closer than they appear. Ladies? Yeah, what is it? Who said it? Clothing store. Now, this one doesn't represent it quite well. This is curved like a sphere. What if it was curved more like a cylinder? So it's only curved left and right, but not up and down. So it's flat up and down. So if you stood in front of a mirror, you would look the same tall, but skinnier. And so department stores love to put these in their dressing rooms. Just enough curvature so you look like you lost 5 pounds in that outfit.